All right, it's 6:30, so we're going to go ahead and get started. I want to thank everyone for being here tonight. This is part of the Our Earth, Our Home series, which was co-created by WSU Extension Island County and the Camino Island Library, which is part of the Snow Owl Library chain. Back in 2019, and one of the silver linings of COVID is that we've been able to move this online and expand our reach from Camino to the rest of Island County and beyond. So this evening, we're still just in the meeting controls, but I have everybody's video and chat turned off for now. We might turn those back on for the Q&A session. But in the meantime, you can use the chat function to ask questions, and we can get to those at the end. So I wear a couple of different hats for WSU Extension Island County, but I'm here tonight representing the Island County Shore Stewards program. If you haven't heard of it, it's a great educational program for those who live on shorelines, those who live near the shore or on bluffs, or really just anyone who's interested in learning how we can take care of our properties in a way that helps the environment, because by being good stewards of the land, we are good stewards of our surrounding water. So if you sign up, you get a copy of our peer-reviewed publication, Guide to Shoreline Living, that has 10 different guidelines on how you can take care of your property. You'll also receive 4 to 6 newsletters per year where I write about different shoreline living or related topics and send those out. And you'll also receive emails letting you know about events like the one tonight, as well as workshops and other events that we put on. I'm also excited to announce that we have another one of these coming up on November 18th with Dr. Jan Newton. She is an affiliate professor at UW in the School of Oceanography, as well as the School of Marine and Environmental Affairs. And she also works in the UW Applied Physics Laboratory. So she's going to be talking about the efforts going on to observe the occurrence of ocean acidification in Puget Sound and what the impacts of that are. So I will put the link to the registration in the chat for anyone who's interested, and I hope you can join. But before we get to that, I have the privilege tonight of introducing our speaker. Dr. Debra Kelly is a professor in UW School of Oceanography, and she's also the director of the underwater cabled component of the National Science Foundation's Ocean Observatories Initiative. In the course of her career, she's done some really incredible things, including going on over 50 dives in a 3-person submersible named Alvin to depths of 13,000 feet. And as a professor, she also shares her knowledge with students both in the classroom and providing opportunities for them to take part in research expeditions at sea, which I just think is so cool. So with that, Dr. Kelly, would you like to take it away? Oh, I think you're still muted.
There. Better?
Yep, perfect.
Okay. So I work with a ton of students and a lot of folks. So I'm pretty informal, which happens when you go to sea. So if you want to address me, or you can just ask a question or call me Deb, I don't care. Anyway, so I wanted to give you an update of first, for folks who haven't seen some of the work that I do, how we access the sea and how that's changed since 2014-ish, and give you some insights about the most active underwater volcano off our coast. And it's the only active volcano in the whole world right now that's instrumented with the internet, basically. So I would like to share that with you. So my hopes for this presentation are that where I'm fortunate enough to work, it is the most active volcano. We work anywhere from about 10,000 feet off our coast to the top of the volcano. And we see a lot of amazing habitats, but I wanted to share with you Axial Seamount today because it is such an amazing place. Since 2014, we basically brought the internet into the ocean with a lot of power and bandwidth. And so all of the data that are coming in from our underwater observatory are open to everybody in the world, which is relatively novel. And that observatory has definitely changed the way that forever, how we're going to interact with the oceans. And there's many of these observatories connected by fiber optic cables to shore that are either in the planning stage or installed in the world right now, and they will continue to grow. So when I grew up here in Washington and used to like to still do hike around the Cascades, and was always aware about photosynthesis and the sun and all the processes that it drove on Earth. But I did not understand or wasn't aware of that there's this whole other energy source coming out of underwater volcanoes that fuels a substantial ecosystem that most people don't know about, and is, in my view, one of the areas where the most important discoveries in the oceans are going to be made. And what I'm talking about is mid-ocean ridges. And this is where 70% of the volcanism occurs on Earth. And most people never get to see it because they're a mile, 2 miles down, something like that for these volcanoes. So I wanted to share with you this environment because it is amazing and almost nobody ever gets to see it. So why I had a very diverse background growing up. My dad finished 8th grade. My mom finished high school, but I was the first, well, myself and 2 siblings were the first to go to college out of all the extended family. And I started out as a music major, then a Russian major, then a graphic design major. And when I was a senior here at the UW, I switched to geology. And was always interested in Cascade volcanoes. But to put myself through school, I started working for a professor here named John Delaney. And the first year I worked with him, he said, "Would you like to go to sea?" And that has resulted in totally changing my life. So I always think it's important thinking about why people do things. And so I wanted to share that with you. So about over 70% of the world's volcanism occurs underwater. So it does govern in a huge face of our planet, right? The place where that volcanism occurs mainly is the mid-ocean ridges spreading centers. It's the longest mountain chain on Earth, and I'll show you a little map of that. There's hundreds of thousands of volcanoes, not even connected with the mid-ocean ridge systems, and we've only investigated a few of those. Surprisingly, even though volcanism underwater is such an important part of our planet, because they're very inaccessible and normally we have no idea these volcanoes are going off, there's only been about 3 times when we've been able to witness with the robotic vehicle these volcanoes. They've been mined. They host underwater hot springs, which is an incredible resource for copper and gold and arsenic and mercury. And there's in my students' lifetimes, they're going to have to deal with mining some of these amazing ecosystems and the choices that we have to make on our planet about resources. The hydrothermal vents or underwater hot springs that are driven by the volcanoes are some of the most amazing things on our planet, the most extreme environments on Earth, and host amazing life forms. And I'll show you that. But they can also be extremely hazardous. And for example, off of New Zealand, there's a whole chain of underwater volcanoes. Some of them are quite close to the surface, and it turns out the cruise industry, once they realized what was going on, actually changed the path of the cruise ships to not go over these volcanoes. It's a little bit of an old animation now. Some of you might have seen this before. This is from satellite data, but I think it's very compelling. The face of Mars is mapped better than our own planet, which is always interesting to me, the choices people make. And this is very low resolution satellite data, quite low. But what it shows is all these little pinnacles here in different colors. The dark blue are quite small, maybe a couple kilometers in radius. And then as you get to the warmer colors and eventually white, you can see the Hawaiian volcanic chain coming up here. And so there's hundreds of thousands of these volcanoes. They host incredible biological communities. They have minerals that are of interest now for mining. And yet we've only visited in detail a few of these volcanoes. And so in the thinking about, what I share with my students, where they want to go with their lives, there's huge opportunities for making important discoveries about these systems yet, and making political, societal choices about what we want to do with our planet in the future. So this is a map. Maybe of you have seen this. So you strip off all the water and you'll see that red line that is wrapping around the planet like a seam on the baseball. And that's where the underwater plates or the tectonic plates are spreading apart and where the volcanism occurs. Much of the volcanism occurs on our planet where the hottest rocks on Earth are being formed actively every day. And you can see if you, these are the ocean basins. So 70% of the face of our planet are ocean basins. And this is the process that I study is a major, the most dominant process that forms that part of our planet. So if you look up in the little, the upper right-hand corner, right above rocks, that's the one-if-you-could tectonic plate there. And this is, that you can see this here. And so this is the building blocks. So they're kind of like a jigsaw puzzle. These big plates wander around on our planet, evolve over time. And luckily for us, we have a quite small tectonic plate there in red. And because of that, it's a perfect size to study a lot of the processes that are going underwater by putting in this underwater observatory, which I'll show you in a minute. And we can actually reach it. It takes a day and a half for us to get here from Seattle. And so it's this really amazing opportunity to study in detail a lot of the processes that operate on our planet. And now we're being able to study them in real time. And I'll get to that in just a sec. So I was going to point out that there are places on land where you can study these. This is the island of Iceland, a gigantic seamount. And it's a place I love to go because it's right where the Mid-Atlantic Ridge is splitting this long-lived underwater volcano in half. And so we can take students there. And in this case, at Rift Valley is where on one side of a tectonic plate, it's where volcanoes are occurring, and then the North American plate. And you can walk around what is, if you could strip off all the water, this is what the seafloor would look like under there. And it also has a really nice hot spring system. And so by going to places like this, we can gain insights to operating processes that are operating underwater. So we can go on exposed sections of ocean crust. There's places in the island of Cyprus and Oman and Iceland, but a lot of the biological magmatic connections that go on, volcanic connections are underwater. And again, most people never get to see them because everybody can look at the stars and recognize that there's a solar system out there, but it's very hard to obviously see through the water. So I wanted to share with you a little bit of how we get to the seafloor and how that's evolved over time. So at the UW, thanks to the state of Washington, we got the first global class research ship, the UW RB Thompson. These are about 270 some foot long global research ships. There's a companion ship operated at Woods Hole. When I first started going to sea, my mom thought that when I said I was going on a cruise, she thought it was a luxury liner. These are working class boats. So we get on the boat and we have to bring everything from toothbrushes to computers to all of our gear. They're really nice boats, but they're working class boats. So cabins are not what you might see on a research or a cruise ship. The tanning salon is basically, we call it the steel deck out there. The first class cabin might have a window, sometimes not. The main, if we're not using the whole main lab, their main recreational facility is a ping pong table, which when the ship's rolling 30 degrees is an interesting endeavor. They're expensive to operate, about $70,000 a day if you have a robotic vehicle or submarine on them. And because of that, these are funded by the National Science Foundation largely. It's a very long process to get, you can imagine 30 days out at sea, it's very expensive. And so there's a very long review process to make sure that we're doing the best science. These are funded by taxpayers' money. It goes through Congress. And so there's a lot of work that goes in to make sure that we're doing the best work that we can and using these ships very efficiently. Off our coast, which is where I often work, I work a lot of other places. Because the ships are expensive, we always use the ships 24/7, day in, day out, day night. Our weather window off the coast, as of today, it would be, I would not want to be out there at all. Typically, it's June to September. If it's blowing around 25 knots, 25, 30 miles an hour, it's really not you can't do any work out there. It's not safe to be on deck. And so that's what drives our weather window. And of course, safety is everything. So everybody on the boat, including students, everybody goes through a pretty decent safety training. And the image on the right there is us getting into Gumby suits or survival suits, which is always a fun experience for students and a lot of Kodak moments for that. I've had the pleasure of early in my life, starting in the 80s, of diving in the 3-person sub called Alvin. It's the main workhorse for the US for a deep diving submarine, meaning that it's not connected to the ship at all. It's run off of marine batteries. There's a pilot and typically two scientists. All of my dives were, the deepest dive was over 4,000 meters, so 14,000 feet. And it just got upgraded to 6,500 meters. So this next month, I think it's going to have its first dive to 21,000 feet. It's a really great vehicle. I love doing it. Something is very different when you're diving on near the seafloor at those depths inside basically a titanium sphere. It's a very safe vehicle. Like I said, I've had over 50 dives in it. It must be up to, I don't even know how many dives it's had now. It just got upgraded to 6,500 meters. It's a very different environment. So basically you go in through that orange, I'll show you a video in just a sec. There's an orange sail on top. It's opening to the sub. And you crawl in through a relatively small opening hatch into this titanium sphere that's about 6 feet across. The image of me on the left there bottom is in the old vehicle. That one was pretty cramped. The person I used to dive with a lot was over 6 feet tall. The only place you can stand up vertically is right in the center. There's lots of bells and whistles, and basically you're laying on a little floor, kind of curled up in a fetal position for 6 to 8 hours at a time. There's a CO2 scrubber right behind my head because as you have 3 people in a small sphere, you got to scrub out the CO2. And it's hard to, it's also cold where we dive. It's the waters are near freezing. So my analogy is, and when I first started diving, we didn't have any maps, and you can't see very far in water. Light doesn't transmit very far. So at depths of 7,000 feet or so, it's near freezing, it's dark, it's cold. And so my analogy is that having done a lot of hiking in the North Cascades, imagine getting in a Volkswagen Bug and open all the windows at night in the winter and use a flashlight without any maps and try and figure out where you are, and sitting there for 8 hours or something. That said, it's a phenomenal opportunity, and I would drop anything to dive in it. This is, but more and more now we're going to robotic vehicles, and that's because Alvin works, it goes in the water typically around 7, well, the pilots get in about 6 o'clock in the morning. We would normally get in the sub around 7:30. The vehicle would go in the morning about 8 in the morning, and then you have to be up by 4. It can pick up about 200 pounds, but it has to be on deck around 4 or 5 in the afternoon. And because it's battery operated, depending on how much you drive around, it's limited in its capabilities of how long it can stay on the seafloor or dive along the seafloor. So if you're driving a lot, lifting a lot, the dive might only be 4 hours. So more and more since about 2000-ish, we started using robotic vehicles. They came out of the oil patch. And that's because they have a lot of the same functionalities as Alvin does. They have force feedback manipulators to pick things up. They have lots of cameras. But the difference is that they're connected to the ship by a fiber optic cable. So they're not power limited. You can stay down for 24 hours, 3 days, whatever, until your operation is finished. And the other difference is that it has multiple sensors, probably 15 cameras now, sonars. And because it has a fiber optic cable connected to it, all those data are transmitted in real time to the ship. And what that means is it can stay down for a long time, but it also means that instead of having 3 people in a sub, you can have 20 people in a control room, including students, and everybody interacts. So it's a much more multidisciplinary, much more opportunities to engage with a lot of different scientists and researchers and students, and have important dialogues that go on. The other difference is that now we're connecting the ships to satellites, and the satellites transmit all of our video imagery from the ship to shore. And so all of our programs now in the summer, whenever we're in the water, actually just driving with the ship, all of our imagery, video imagery cameras are streamed live to anybody in the world. And so as we dive to the seafloor, you can see us operating, and I'll show you a bunch of that video, operating on the seafloor, and you can see all of our successes and when interesting perturbations happens on cruises, which often does. What I will share with you is a lot of the major processes on our planet undergoing like a storm right now. You can't be on a ship out there. You can't make some of the most important measurements because you're locked inside. Things like underwater earthquakes, tsunamis, gigantic storms that incorporate CO2 into our ocean. Many of these processes go on, and we're never in the right place at the right time to make sustained measurements. And this is the slide on the image on the left there is a underwater hydrothermal hot spring. It's a metal sulfide deposit, and in 1998, we cut it off with an underwater chainsaw and came back 2 days later, and that rock, which hosts microorganisms, had grown 6 feet. So there's lots of things that operate in our ocean, and we're just not there in the right time to make the right duration to make important measurements. And I'll show you some video of one of those perturbations is off of our volcano, on the volcano offshore, where after one of the eruptions, there were billions and billions of microbes streaming from the sea floor. And this was the first time it had ever been streamed live, and the best imagery. It's only been seen a couple of times in our worlds, but it may be an important source for life on our planet that is really not well investigated or understood right now. So lots of important things for understanding how our planet works and making really incredible discoveries. So starting about 20 years ago, John Delaney, who's a professor here at the UW, I used to dive with him a lot in Alvin, and we worked in one of the most active hydrothermal systems off our coast off of Vancouver Island. And we would go out there every year in Alvin or using a robotic vehicle, and these really important changes would take place. For instance, a 150-foot hydrothermal chimney fell over, but we're not there to see what happened, right? And so he started, this was about the same time internet really started taking off, and submarine fiber optic cables were starting to be laid in a big way across the ocean. And so he started a program with a lot of help, a lot of involvement from other places, to basically string underwater fiber optic cables across the Juan de Fuca plate with instruments and moorings. And with a lot of power, and what that meant was we could connect all this infrastructure to the cable and have 24/7 data streaming live at full capability. Because before, when we would put instruments down either in the water column on a mooring or on the sea floor, they were all battery driven, and there was no way to test them when you put them on the sea floor, and they were limited for how much memory they could hold, for how much storage. And so you might get a once in a chance lifetime to put instruments on the sea floor, and then you would come back the next year and try and recover them and find out, well, guess what, they flooded or whatever, and that whole years of data was lost. So John was instrumental in bringing the community together and installing what led to the installation of the most advanced observatory in the world's ocean that spans the coastal margin off of Newport, Oregon, the subduction zone, which people know about for magnitude 9 earthquakes that will happen at some point, and then out across the Juan de Fuca plate, which is a rather benign environment, out to the spreading center where Axial Seamount is the most active volcano off our coast. So I'll share that with you in just a minute. This is just some factoids. So we bring, it's a very high power system, which the normal telecommunication and submarine cables don't have to deal with because they don't need a lot of power. What they care is petabytes of data transmitting over the fibers in the cable look like a fishing line almost. But to drive all of our infrastructure with NSF funded this for 25 years at least. We wanted to have enough power so we could add extra instruments as technology evolves onto the cable. And so there's these, if you look at this map, this is the span of the cable in our different sites that we operate in. And those orange junk boxes I'll show you are these big substations on the seafloor. They're about 18 feet across. And we have a variety of those. And then the Applied Physics Lab has built smaller substations called junction boxes. And we put those in the key experimental sites to study the processes. I'm not going to talk about the water column, what's happening in the ocean off our coast, but we put the most advanced moorings in the world's oceans. They have profilers that go up and down through the water column. All instruments are full out, meaning that they can take measurements from everything from 1 second intervals to 240 a second. And the reason that we put them out there is because our coast is, Jan will talk about it, but it is profoundly impacted by ocean acidification. The coastal waters are some of the most productive in the entire world's oceans. There's events where low oxygen waters come off our coast and kill a lot of the benthic organisms. So there's many reasons to understand what is driving these changes and how they impact the biology and chemistry of the ocean. And right now, this is a little bit out of date. We have over 150 instruments that operate, stream all data at the speed of light to shore 24/7. And the big thing that I want to take home to you guys is it's all open to anybody in the world. So anybody can log on, they can see our underwater video that we stream live and get access to instrumentation. And I'm 60 something. So my next 10 years, one of the things I really want to do is work with students and the public about how we can make these more understandable to everybody and help get the message of how important the oceans are and why they're important, and also to have new eyes, because we all have biases. And so it's always really important to have people that think differently than us and can look at data in different ways. So it's, for me, working in the ocean, I did a lot of walking across volcanoes on our continents, right? But working off the ocean, you're just sitting there on the surface and you could park anywhere. And it's very hard to get a sense of scale. And so what we did here is we flipped the footprint of the underwater observatory from Seattle and flipped it going east. So it's a 525 kilometers of high power cable going on one link anyway. And imagine if you've ever driven across Eastern Washington or across the Cascades volcanoes, there's a lot of really interesting topography there. And so imagine if you're in a helicopter in the dark or above the clouds and you can't see the basalts in Eastern Washington across the Columbia River Gorge, and you're laying fiber optic cables. And if you lay it on sharp surface or rugged surface and it gets a nick in the cable, then it in our case, seawater can get in and kill the cable. So it's a really amazing engineering feat. And since 2014, it's been operational and we've never had any problem with the cable. This year was the first year we had a problem with one of the substations, but never any problem with the cable. So it's been a really important workhorse for streaming data to shore. And I'll share some of the data. So it was installed L3 Meripro, which is a big international company. They were instrumental in partnering with us to lay the cable. This is a cable ship to Dependable. And this is the size of the ship that lays all the cables, submarine cables offshore now. Most of them are laid off of Oregon. And the movie on the right, on the left there is our underwater substation. So these are big boxes. Basically think of a power outlet that comes to your wall, except they can be 9,000 feet down and they're sitting in seawater and they have 10,000 volts. We can turn it on and off. And so how do you plug in cables to that wall socket when you're that deep? And so we used engineering that came out of the oil and gas field. They have these underwater connectors. And every time the robotic vehicle plugs a connector in, it squirts out a little bit of oil, and that prevents any seawater getting into the system. And they're good for about 100 hookups. And we've been delighted with how they work. So this is one of these big substations. And then they're very expensive. And so to get to our main work areas that are like on the top of Volcano, we use smaller substations. And these are all built by the Applied Physics Lab here at the UW. They're built by engineers from day one. John and Gary Harkins, who was lead at the Applied Physics Lab on this program. Because we're an educational institution, they always wanted young people to be involved and basically figure out how to build these things from the bottom up. So we have a long history now with the engineers and new engineers coming online. And one of the great things about this, rather than going to industry, is we're very flexible and can change our designs very rapidly to modify the system to new technologies. And also as more and more researchers want to add instrumentation from outside funding, we have programs from Germany, NASA, National Science Foundation, other places, we can modify our structure to ensure that we get the newest technologies onto the network. So this is just the footprint again, and I just wanted to emphasize that this was there was over 270 researchers that were involved in submitting the original proposals that drove the design for this underwater observatory, and it basically tries to look at almost every process that you could imagine in the ocean. We're able to look at off our coast because of this cabled observatory, and I'll show you a slide at the end that this is really where the world of oceanography is going in a big way right now. And then one of the main design features was, again, we wanted a lot of power and bandwidth because recognizing that a lot of people would like to come over this 25 years and add new capabilities to it. So I'm going to let you go to Axial Seamount now. As I mentioned, it's the largest and most magmatically robust volcano off our coast. It rises to a depth of about a mile beneath the ocean surface, and it's located almost 300 miles offshore. It erupted in, it's kind of a catch-22 if you want to understand. And remember, over 70% of the volcanism on Earth occurs in these environments. But it's a little bit of a catch-22 because if you want to understand these underwater volcanoes, you have to put infrastructure on top of the volcanoes. And you know, if you go to the Atlantic Ocean, it might be 50,000 years before they erupt. So we wanted to pick a volcano that in at least my lifetime, somebody's lifetime, would erupt. And so we picked Axial. It's also one of the best studied volcanoes in the oceans. NOAA had a long-term observatory there that was uncabled. And so it erupted in 1998, 2011, and April 24th of 2015, and it's poised to erupt again. So what we're trying to do is put infrastructure from a community-driven project to look at how volcanoes will work, how earthquakes impact the volcano as a whole, what the lifetime history of that volcano is, and then when an eruption occurs, how does that impact the hydrothermal vents and all the biological communities associated with that. And it's been a spectacular success, and I'll share some of those results. So there's been a ton of work. I think it's probably the best image volcano in the world's oceans now. There's been a lot of seismic imaging, the kind of seismic imaging they would use in the oil patch. And so they are able to penetrate with acoustics down through the volcano into the core of the volcano, similar like what you would do on Mount St. Helens, and look at where there's big holding tanks of lava. We call it melt or magma when it's down beneath the seafloor. And these magma chambers are pretty shallow, a kilometer or a couple kilometers beneath the seafloor. And melt comes from deep within the earth, and it's been a long time history of melt coming up and collecting beneath Axial Seamount, and that's why it's so large, because there's volcanic eruptions all the time, and so the volcano just keeps growing and growing in height. So we have a really good understanding and vision, or I should say a really good vision of what the subsurface of this volcano looks like, and that helps drive our understanding of how some of the other processes operate there. One of the amazing not two known discoveries, but one of the things I'm most interested in is that and probably the top two least understood things about volcanoes underwater is when an eruption occurs, you inject 2000 degree Fahrenheit melt into the seafloor that is saturated in seawater, cold seawater. And in a variety of places around the world's oceans, we haven't seen one form yet, but through other ways that we can image the seafloor and the water column, what happens is it forms this gigantic plume. It's kind of like a ash plume. It does have ash, but it's not like a eruptive volcanic explosive eruption on land. And this warm, buoyant plume of water can rise 3,000 feet above the seafloor or more. And it trains, it can be very large, 20 kilometers across. They're extremely ephemeral. They probably form within a couple days or a day when an eruption is starting. And one of the, and they carry a ton of heat, lots of volatiles and chemicals. But one of the most interesting discoveries, they also carry microbes up into the water column where they're easier to see and analyze from the deep subsurface. And so when we take a ship out after the fact, maybe 3 months later, and tow instruments through that plume and collect samples, we can get insights into microorganisms that live deep into the seafloor. And I'll touch on that in a few minutes. So we've never seen one active, and we're starting to put instruments out on Axial Seamount to catch one of these eruptions for the very first time. They do impact our oceans, but we don't know. It's hard to measure the specific amount of fluxes and heats of chemicals into them, but they're definitely a major impact to our oceans. So one of the major discoveries to come out of hydrothermal vents in the late 80s, late 90s, or 79 was the first one discovered, is that these volcanoes, first of all, they support life. They are one of the most extreme environments on our planet. The volcanic gases coming out, there's no sunlight down there. So these microorganisms have figured out how to use things like carbon dioxide, hydrogen sulfide, methane, almost any gas, hydrogen, any gas that would kill us. Instead of using sun, these microbes have figured out metabolisms very early on in the history of our planet to use the energy from the volcanoes. So we don't know a lot about them in many ways now. They're very hard to culture. Probably less than 1% of the organisms have ever been cultured. People are interested into pharmaceuticals from the sea, medicines from the sea. They have industrial applications. And I'll show you a video in just a sec. One thing we have started to realize is when there's a volcanic eruption, there's a lot of carbon dioxide, there's warm water circulating in the seafloor, and there's billions and billions of microbes that stream into the world's oceans from this. And they are probably sources for microbes in the base of the food chain that are distributed throughout our oceans. But it's a huge place for discoveries. We started working around 2008, I guess. We started the first surveys for our cable for Axial Seamount. On the slide to the left shows the status of the outline of a very large eruption that occurred in 2011. And we were out there 3 months later we did very, very high resolution detailed surveys of the top of the volcano to try and figure out where to lay the fiber optic cables. And during that survey, where all those orange dots are, we came across these very large pits, collapsed pits in the seafloor. With all that white material you see are billions and billions of microbes streaming from the seafloor, as well as their byproducts. Some of them are high temperature organisms, meaning that they require over 90 degrees C to live in the sea subsurface. They cannot live on oxygen. So we know that they come from deep in the seafloor. And there's some interesting stories about those. So this was, I'm gonna speed this up in a minute because we take a lot of students out to sea, and we were doing an engagement project trying to share with them the impacts of pressure. So the top of the volcano is about 150 times pressure. So we take styrofoam heads and this is a time lapse of shrinking styrofoam heads and cups, and you can see that. And then this is the surface of the volcano. Those are lasers from the submarine. And what we're looking down into is basically a fossilized lava lake like you'd see on top of Kilauea. And as the lava lakes form, because they come out 2,000 degrees, the cold seawaters near freezing, the top of the lava lake freezes over. And then lava under the top of the lava lake exits other places on the seafloor, and you're left with this void, and the whole top of the lava lake collapses. This is a big column, and you can see all that rubble pile from the top of the lava lake. So we were driving across these lava lakes, and then we came up on these features. You can see all this white material. The collapse zones are amazing. There's a big arch there. All that yellow material or brown yellow material is microbes. And so when NOAA first dove on this, they were the first ones out there, and they've been out there every year. They're like, what is this? This looks like old rock. But they knew they were in a place where they had been last year. And so they figured out that there'd been this very large eruption. And when we were out there, we came up on these big collapse pits, and I'll stop zooming through here in a minute. And this is what we saw. So these are big, what used to be lava lakes, and all that white material is very thick microbial mats of both very high temperature organisms, lower temperature organisms. And for probably months after the eruption, there was this huge ejection of biomass from the seafloor. You can see this shiny surface here when the lava erupts. It's again 2,000 degrees, it hits freezing seawater, and the top surface turns to glass. And this is one of those collapse areas after 2011, and you can see it's already colonized by very thick communities of microorganisms. And there's only been, well, we've seen them twice at Axial Seamount here in 2015, once in 1991 off of Mexico, and then once off of Vancouver Island. This is an underwater hot spring that has been studied for years, and it was completely covered by the lava flow. And 3 months later, so this was total bare rock. 3 months later, life is completely thriving. So these are filamentous bacteria that looks like hair waving in the wind. I'm gonna back up just a sec here. Hair waving in the wind. These small blobs here are limpets. And so life just comes back amazingly fast in these environments that have been perturbed by these underwater eruptions. And so this is one of the most, if I could, go on a volcano for many, many years underwater, this is one of the main things I would study, because it does have really important ramifications about life on our planet. And there's only been 4 places where we've ever been there after the fact, looking at these things. And so one of the main drivers for our infrastructure on Axial Seamount is to be there the next time Axial Seamount erupts and monitor all these processes in time. And maybe these are predictive of volcanic eruptions. So you could imagine a scenario like a red tide where the volcano hasn't erupted yet, but it's starting to crack, earthquakes are happening, and a lot of CO2 goes into the subsurface, and the microbes just go crazy. And so maybe we could use the microbes coming out of the seafloor as a precursor to when an eruption might take place. So
visualize the most extreme environment you can imagine.
In 2000, we took a bunch of students out with us, and 3 of them were in a class I took. They'd never been out to sea. It was their first introduction to hydrothermal vents, and they wanted to make an engagement video to share their insights into underwater hot springs and why they're so novel. And so they never made a video, hadn't had any experience. It's about 3 minutes long, but if you haven't seen these environments, I think it gives you a really good insight to how they form, why they're important, and has some nice imagery. So
Imagine. What do you see? Mountains, deserts, glaciers? Maybe places like these come to mind. Places with harsh climates, scarce food, and no water. But what about a place like this? Located 300 miles off the coast of Oregon, an active underwater volcano called Axial Seamount protrudes from the seafloor, looming thousands of feet above the barren seascape. This dark setting has never seen the light of day, as sunshine barely penetrates 600 feet into the ocean. At these depths, there are conditions rarely observed on planet Earth. The pressure due to the overlying ocean is 150 times what humans experience on land. That much force is equivalent to having a Boeing 747 jet on your chest. Temperatures here are cold and constant. Throughout the year, day or night, the water lies just above freezing at 34 degrees Fahrenheit. Suddenly, sharply jutting up from the seafloor are columns of rock towering over 5 stories high. These pillars can be enclosed in so much bizarre life that the rock itself isn't even visible. And the strangest part about this ecosystem? Fluids reaching temperatures of 660 degrees Fahrenheit are continuously flowing out of these chimneys. That's over 3 times the boiling point of water at sea level. Indeed, some of the microbes thriving near the vents have the highest temperature tolerances of any organisms known on Earth. These structures are known as hydrothermal vents and are found in the caldera of Axial Volcano. Hundreds of similar vents are found in every ocean around the world and are created when seawater seeps miles down into the ocean floor and becomes superheated by volcanic magma, forcing it back upward far from where it entered. When the metal-enriched fluids meet near freezing seawater, they lose hold of these minerals and produce deposits that eventually build up to form these great stone monoliths. A mile beneath the waves, this thriving ecosystem can't depend on the sun for photosynthesis, as almost all other life does. Instead, the organisms living in total darkness need another source of energy, a source that comes from below instead of above. Bacteria harness the energy from the toxic chemicals seeping from deep within the underwater volcanoes through a process called chemosynthesis. The success of this entire ecosystem is reliant on these bacteria, as they are the base of the food chain. This environment is an obvious competitor for the most severe that the world has to offer, and yet its various processes are poorly understood at best. Novel instrumentation is currently being deployed into the ocean to provide high-quality data in hopes to better understand this underwater oasis of life.
So I thought they did a great job. If you can, I have about 10 minutes left. I know it's a, but I'll hang out for questions. So this is one of the vents on top of Axial Seamount. They're really beautiful environments. When I first started diving in the sub, there's really very few particulates in the water down there. This is, again, about a mile down. And you sort of forget that you're in water, but you can see these animals there. There's all those brown things are worms. There's red-headed worms. They really are like fire hoses coming out of the sea floor, and that smoke is fine-grained metal sulfides, pyrite, things like that. And these fluids are the base of that's what provides all the energy to the microbes and all the animals that live down there. So they're really gorgeous. Deep in the ocean, there's almost no color, but when you come up on these, they look like oases. There's bright blue protists and ciliates, and then these other animals that live there. And if you could put your arm about buried up to your elbow, in that, what you would hit is metal sulfide deposits. So there's a lot of interest in mining these systems now, which should someday somebody's gonna have to deal with, but they are really beautiful. They've been going on, as soon as there were oceans on our planet, and the hydrothermal vents have different animals depending on what part of the ocean. So there's very interesting stories about how animals evolve in these environments, and we're still making new discoveries about the animals and what they do there. So hang in for about 10 minutes. This is I'm not going to zoom into this, it's on our website, but the larger animals at this depth, mostly what we see are skate and rat-tailed fish and octopus. And all these larger animals, they swim incredibly slow because the waters are so cold. There's not a lot of food down there. And so they conserve their energy by swimming slow and not using a lot of energy, but they don't show any fear of us when we're diving. Yeah, this is one of the most beautiful. If you look at octopus ballet, it's on the internet, and they're pretty territorial. So often if we go in the same place, we'll see them. So this is a very intense slide, but the only message I want to say is we worked with a bunch of scientists. The PN3B there, that big orange box, is one of these big primary nodes, and then the yellow boxes are our smaller substations. And the only thing I really want you to take through is there's a lot of instrumentation out there that looks at seismic events, high definite imagery coming off the hydrothermal vents. I'll show you that. Hydrophones, so we can listen to mammals. We can actually suck in fluids from the hydrothermal vents and filter out DNA from the microbes. So we're looking at the evolution of microbes over time and how this whole volcano changes over time. And again, all these data are open for you guys to look at whenever you want. So I'm going to zoom into Ash's hydrothermal field here and show you a HD camera that we have out there. again, 300 miles offshore, a mile down. And this is what it streams every 3 hours for about 14 minutes. And if you go on our website, Interactive Oceans, you can see this. And every day we image the same part of this underwater chimney, which the whole mosaic is shown on the right there. And we photo mosaic it or image it every single day. And what we're doing is looking at the change in growth of the chimney over time, metal sulfides, and how the animals evolve over time. Twice a month, we stream it for 24 hours and once a month for 3 days, because we're interested, some of the fish, well, all the fish have eyes. And so we're interested to see if the impact of light has any impact on the animals. Doesn't seem to be right now. And I should say also there's studies going on that some of the organisms on the vents, like shrimp, they seem to see light, but not in the wavelength that we see light. So it's looking at when these vents shut down, how do animals first find the vents, and then how do they wander around the vent system? So lots of interesting questions. So we have this network, and the orange dots are where we have seismometers that detect underwater earthquakes. And in 2015, on April 24th, William Wilcock here at the UW emailed us and said, I think something's going on, and in a 24-hour period, there were over 8,000 earthquakes. They were coming in so fast that it just basically overran each other. And these are small earthquakes, except for a few of them that you would never measure on shore. And this graphic on the right here, I'm going to reverse it here. Oops, sorry guys. So these blue dots are the underwater earthquakes, and this is the caldera, the collapse zone. You can see that, okay, that's when the eruption started. And luckily our infrastructure was still alive. And then this geophysicists started seeing these red dots. And so we knew immediately that there was an underwater eruption going on, and I'll share with you what these red dots mean in just a second. So huge number, thousands and thousands of earthquakes. And this is emblematic of volcanoes underwater all the time. That's what happens. But this is the first time that we were able to ever stream it live and have lots of people looking at it and then be able to respond to that eruptive event. So at the same time that was happening, there were these noises, acoustic vents in the water column. So these are not earthquakes. And what you're listening to is from hydrophone data. And seismologists from Lamont and here and other places started analyzing these data. And by the way, whales out there can hear this. And what these events are underwater explosions. And this will just keep going, and I can't stop it. So I'm going to eject myself just a sec here. And so we dove. The seismologists, they were able to triangulate on where they heard these events or detected them. And all these red dots here up in the upper left here are where they accumulated, where they were able to image them. And so we were out there 3 months later, and a student of mine mapped the seafloor again, and then we dove on it. And lo and behold, this is the eruption. And we dove 30 feet away from, this is old lava, this is all new lava. And we drove up this about 30-foot angle. This is a explosion. These are called pillow basalts. They erupt. If you've seen the underwater eruptions on Hawaii, it's the same thing. And every time they erupt, they explode. So then we drove up on top of this lava flow, and it for acres and acres and acres, it was completely covered in these microbial mats, and there was microbes streaming out of the seafloor. So again, another time when we were able to see the impact of eruptions and generation of life on the seafloor. To give you a sense of scale, the lava flow is over 400 feet thick. So next time when you're in Seattle and looking at the base of the Space Needle, look up, and right where the Space Needle grid's structure spans out is about where the width of the depth of the thickness of the eruption was. So pretty amazing. Just a couple more things. So so there's that right there. That's a image of that. And then the same thing, there was another, a woman scientist up at WSU or at Western Washington. She was able to use the acoustic listening system and pick up a different kind of signal. It wasn't these punctuated explosions. And she had done a lot of work on eruptions underwater in Hawaii. And what she determined was even a mile beneath the sea surface, that there was fissures that opened up and lava fountaining on the seafloor, which to me is still amazing that there can be enough pressure of melt ejected into the ocean. And when we dove on one of our instruments, that brown material there on that yellow platform there was actually ash. So there was more evidence that there was this really explosive or relatively explosive fissuring eruption on the seafloor. Two more things. So at the same time that there was over 30,000 explosions, the seafloor, there were over 8,000 earthquakes. At that 24-hour period, the seafloor dropped almost 7 feet. And they've seen this, Bill Chadwick at OSU has seen this before. They had battery operated instruments out there, and they caught an eruption in 1998. So this is the seafloor depth, about not quite 1509 meters beneath the ocean surface. And it's a flat line almost, not quite. And then during the eruption in 2015, it fell almost 7 feet. And then you can see it flatten out again. And we see this pattern over and over again. In 1998, the seafloor fell dramatically, 24 hours. And then as more and more melt is injected into the subsurface of the volcano, the seafloor deforms just like Mount St. Helens, it rises up. 2011 eruption, 2015 eruption. And because we have the cable network out there, we can Bill is probably the first place in the world's oceans where we can predict when the next eruption is going on. And so he keeps this, you can go on his website and it updates every single day. And now, right now, you've seen we surpassed the rise in the seafloor for the 2011 eruption. And now we're looking out towards the 2015 eruption and past. So probably sometime between 2025 and 2029 is when the eruption will occur. And one of the guidelines of, as we get closer and closer, the amount of earthquake activity is going to increase phenomenally as that starts to happen. So, so just a couple more. So one is the world is changing. How we look at our oceans is changing. You may or may not know that most of the communications in the world is not through satellites, it's through submarine fiber optic cables. So there's lots and that technology is evolving incredibly fast to using cables that actually become sensors. So you can imagine, 3,000 miles of cable on the seafloor that's actually sensors. And this just shows a pretty updated graph or image of where there are submarine observatories planned or installed as it stands to date now. We do take, I wasn't sure of the audience, but one of the things I'm most proud of and that I lead is we do take a lot of students to see undergrads from across the US. It's a simple application process. And they go to sea with us for 8 to 45 days to develop science and engagement processes or projects. And we work with them from a few months to 4 years, depending on what they want to do. And there's no requirements, and they just get a good sense of why we do what we do, why the ocean's important, and what it's like to go to sea. So everything from art people to art students to music majors to I've had people that went in to become doctors, and it's a really amazing opportunity. And I always get humbled, and I love going out to sea with them. They've developed, so we have a lot of resources. I can send this to you guys online, but we have a great image gallery with video, a lot of information about our site. The students have produced a really phenomenal biological catalog for animals underwater off of our coast, as well as far up, like on the margin, near coastal waters, and then far offshore for axial. So all the imagery, almost all I've shown you today is on there. And then we have hydrophones out there that are, they can listen to mammal calls. And this is also coming in live. And one of the coolest things, I'm not a mammal person, I just study volcanoes. But anyway, William Woolcock and his students have been looking at these data for over 10 years at Axial Seamount and looking at the they can listen to, in this case, fin whales over the volcano. And one of his students did a long-term analysis, about 10 years of the whales. And what she determined was that the whale calls or the songs are changing over time, and it doesn't seem to be impacted by increasing noise from ships. They're actually getting quieter. And so one of the hypotheses that's my favorite is that as the whaling industry, as there was more restrictions on whaling, that the fin whales have, their population has increased. And so I always like to think of it, maybe they don't have to yell as loud to talk to each other. So that gives me great hope. But this is also accessible. And then I think I'm done, just to say that thank you. And we've taken a lot of students to sea with us, over 160 students. And I'm very proud. They've become high school teachers, writers, almost any field you can imagine. And that was my hope for them. So I know I went a little bit over, but I'm way open for questions. I can sit here for a while and take whatever questions you have.
All right, thank you so much. That was so informative and just visually stunning too. So well done, thank you. We have a few questions here. If anybody doesn't want to type into the chat, I've also made it so that you could unmute yourself and ask as well. The first question we have is, how has this data been used to initiate research into other areas of study, such as medical or industry innovations, geology predictions, etc.?
Yeah. So I'm not a microbiologist at all, but I get to by osmosis learn things, and so there's not just from hydrothermal vents, but there's a significant amount of energy going into look at pharmaceuticals from the sea for cancer research, for example. And so one of the interesting things to come out of hydrothermal vents is that, the vents, actually, that's how all the things you hear in the news about processing DNA and how people are able to look at the COVID virus so quickly through PCR analyses, that came out of a hydrothermal vent organism. So it really changed how we look at our, analyze a variety of things. So pharmaceutical companies, because some of the organisms live at very high temperatures and high pressures, when they bring them up onto the ship, for example, and stress them out because they're no longer in the environment, they produce different kind of antibodies. And so there's some interest and research going on into new pharmaceutical from the seas. Also because these organisms live at very high temperatures, over 200 degrees Fahrenheit, and they have enzymes that are much more stable. Industry is looking into them for example, processing sugars at much higher temperature because it's much more efficient. Bleaching of genes has been used, is another industry application that came out of looking at these high temperature organisms. And then to me, one of the most interesting ones that has been going on lately, well, quite a few years now, is as we think more and more about how do we carbon dioxide out of the atmosphere, these organisms some of them have super high doubling rates. So, within hours or less, they double in the amount of cells, and they take in carbon. And so there's a lot of bioremediation investigations going on to, the mining industry has used them to extract arsenic out of waters coming out of mining slags, because in the water itself, it's very hard to recover because it's not a solid phase, but these microbes precipitate out, for example, an arsenic oxide, and so you can recover metals from that. So there's if I could go back and be a microbiologist, I probably would right now. So there's so that's going on. We're learning a lot again about how the volcanoes behave over time, how the animals change over time. So I didn't talk about it, but our infrastructure near the coast, we have the highest resolution data of any place in the world, looking at ocean acidification and these low oxygen waters coming ashore. You've probably all heard about, or some of you have heard about the warm blob that came ashore, and we're able to image those far offshore because we have infrastructure at Axial Seamount and see how they propagate onto the coast. And then the final thing that I have great hopes for is that we're very sensor poor in imaging at very high resolution, very small movements of the seafloor. And so as we recognize more and more that we are going to have a mega thrust event across the Cascadia subduction zone that will impact potentially from Northern California to the northern tip of Vancouver Island. And there's a lot of people in cities there with probably large tsunamis coming ashore. What's coming out of the Tohoku earthquake, because there was a cable observatory there and a subsea floor observatory off to Costa Rica, is it looks like there are telltale signs before the earthquakes happened that the seafloor starts moving. And so there's 3 different instruments sitting on top of the volcano because it's more accentuated in terms of its deformation signal that are very, very, I guess, very promising results in being able to image incredibly like sub-centimeter movement of the Earth's surface. And so the hope is to put these instruments along the Cascadia subduction zone and be able to use it as not only to understand earthquakes around here, but as an observatory around the Pacific Rim. And I'm super, super excited to see that, the results from that. So.
You've touched on this next one a little bit in this answer, but maybe you might have something else to add. It says, how are the organisms on the seamount studied? With the pressure differences, can they be brought to the surface? So you kind of touched on that one a bit.
Yeah, and that's a great question. Many of them, they are crazy organisms, and it's really hard to kill them, really hard. And so many of them they don't care about pressure at all, and they are hard to culture. But as mostly coming out of the Human Genome Project, even though they're hard to culture, the technology for looking at the genetic makeup of these organisms is just exponentially growing. And so they're getting and I don't have a clue. I can look at the data, but I don't know how to make sense of it. But the microbiologists are, it actually redefined how they think of life and how it's split off into different life forms. And that came out of a hydrothermal event. It's a paper a few years ago, and I can give you the link about that. So the tree of life has fundamentally changed over the last 10 years because of that. And so one of the technological advances is that we know when, the question is, if you bring something up from deep within the ocean and you bring it through, oxygenated seawater, what are you missing? And so there are new titanium capsules that we can capture the fluids in situ on the seafloor, secure the bottles, tighten them under pressure so they never get depressurized, bringing up onto land, and then keep them under pressure. They can do it for animals too, like the tube worms, and then grow them in situ under those pressure temperature conditions. And so it definitely does add new information and change, in some cases actually changes what we see if we were just to take a unpressurized sample and bring it up from the seafloor. So those technologies are definitely growing.
All right, this next one is about the Sea Experiential Learning Program, or maybe other similar ones out there, but April's asking, the program has taken teachers to sea too, is that right?
That's absolutely true. And so when I first, this was in the 90s, the UW had a program called Revel, and we took over 80 middle and high school teachers to sea. So mostly we take undergrads, but we do also take teachers once in a while. And if a teacher is interested in doing that, just give me an email and I love having teachers at sea. And what I hope is that teachers gain from that experience and then figure out how they can incorporate that into the classroom. And this year we just got funded for an NSF program to work with teachers to how can we bring our data in a meaningful way into K-12 and inform students about processes or questions, how you look at data in the ocean. So yeah, definitely email me. I'd be glad to talk to you.
Great, thank you. We have another one. What temperature can the Alvin submarine withstand?
I actually don't know the upper temperature. So the sphere is titanium. The windows, which the portal when you're diving is that you actually look at is about this big, but on the sub it grows to about that big because of the engineering design for pressure. And one of our jobs when I was diving, we couldn't there at that time when you're diving in Alvin, there weren't any portals looking forward. We could only look sideways. And we used to dive in still the most active, if not the most, probably the second most active hydrothermal sites in the world off of Vancouver Island. And so the pilots can't see, there weren't cameras looking out at the side. And so our job was to look out the windows and make sure that they weren't driving through a hydrothermal vent, so to speak. They do have temperatures on the bottom of the sub, and I actually do not know the upper temperature, but I don't think it's very high. You know, the sphere is titanium, but they have a lot of cabling, and cables don't last at super high temperatures. So it's a great question. I honestly don't know, but I would guess that anything above 100 degrees Fahrenheit, things wouldn't be very happy. So, but they do have a lot of temperature measurements around the sub to make sure that when you're sitting on the bottom or above a hydrothermal vent, that you're not in a place that you shouldn't be. So.
Do we have a warm blob going on this year?
I do not think so. I don't think so.
Yeah, I think that's what I've heard too. Is there a process in place to monitor any impacts that may occur by drilling, etc.? How would actions that harm this ecosystem be halted?
Oh, perfect question. So there's a long-term, boy, must be 50 years old, maybe longer now, international program called it went through different names, Ocean Drilling Program. It's now called the International Ocean Discovery Program. Fabulous science program, probably one of the most historic. We've learned so much about the oceans, climate change, many things about the ocean. And it's a drill ship, just like what they would use it's a converted oil drilling platform. And so it's a very long-term process where scientists get together and put a pre-proposal in, then a full proposal, and then usually another full proposal. And so a group of us, because we know very little about the subsurface of the ocean and the most extreme conditions under which life can thrive, and the organisms beneath the seafloor, and how there's actually underwater rivers that occur in the ocean crust of seawater that have their own microbial communities. There's all these profound questions about how life and fluids and chemistry migrates around in the subsurface. So I'm part of a project that has been very highly reviewed to drill maybe in the next few years. The drill ship is being decommissioned and they're going to build a new one. I'm hoping hopefully in the next 3 years that we're going to drill into just to the side of one of these hydrothermal vent fields, not where there's any animals. And we're going to hopefully, if it's successful, drill around 900 feet beneath the sea floor, and in a variety of holes, one situated near the hydrothermal field and then an array outward. And what you can do with those is you can plug the holes at the top and put instruments down the whole section that allow you to have, if you open valves, you can access the fluids, access the microbes. You can measure seismic events, geophysical parameters, all down hole. And then we're going to cable it. So all those data will be coming in live. So that's going to give us a window into our planet we've never had before. And then the other thing that we want to do, because we've had, and this is done before, hasn't been a cable observatory, but off our coast, they drilled holes on the middle of the Juanifica Plate, and then they drilled holes away from there. and they injected tracer experiments, chemicals that are not in nature. They're completely benign. They don't hurt anything, but they have a very distinctive signature. And then you can look at the holes away from there and monitor basically how these underground aquifers behave, how do fluids get transported. So there is I just finished writing an environmental impact evaluation. The holes themselves are like this big around, so they don't do anything. We're not drilling into a place where there's active animals. There's animals that can migrate away. There's no gigantic noise source. The sediment that comes out around where you drill is maybe 6 feet away from the hole. It doesn't create a big plume. And so the amount of impact it has compared is the footprint's really small. Yeah. So we've done a lot of work to make sure it doesn't happen. Yeah.
Nancy says, so you might connect to our earlier earthquake warning system in the future.
Thank you. Thank you. Thank you. Thank you. Thank you. Yes. So that's, there's folks aggressively pursuing that. And the hope is, so we only have a few seismometers on our network. A sec here, I'll show you because it's easier to talk about it. Yeah, so where you see at the bottom on the thing that says a cable array, and there's green dots with a circle, and you can see the little arrows that say the Cascadia subduction zone, and where there's those triangles, that's where the Juan de Fuca plate is subducting under the North American plate. And you can see it's we're looking at that blue zone is about 9,000 feet deep, and then the warmer colors right by Pacific City is 100 feet deep, right? So you can see it's a pretty steep slope. And then all those dots and boxes are where we have our infrastructure. And there's almost no place in the world on any plate where subduction is occurring, where the big magnitude 9 earthquakes occur, where we have seismometers on the plate that's going down and the plate that's deforming or deforming in response to that. So a huge lesson from Japan, because they are impacted by lots of big earthquakes and that are devastating, and tsunamis, they built a very large observatory underwater called DONET. It's an operational observatory, so even though they're getting great science, it's more like the US Weather Service. It's not strictly for science. Ours was dedicated to science, although we can image earthquakes and tsunamis very well with it. And so we would like to be proactive and enlarge this system to span Northern California and work with Canada to, they have where it says ONC up there, they also have a cable observatory, and create a offshore early warning system that spans from Northern California clear up to Vancouver Island. And the reason for that is because it's harder to locate earthquakes offshore, and there's a delay. And so if, and on the big, like when Cascadia broke last time in 1700, I always think of it like an unzippering, where the magnitude 9 earthquake propagated from the south all the way up, right? So it split open the entire Cascadia subduction zone. And that process, if it starts in the north to reach to Seattle, that process of when the seismic waves, the bad ones hit, is around 4 minutes, something like that. And so depending on when the earthquakes, and because data from the cable array go at the speed of light, we would know instantaneously where the earthquake was. We would know the magnitude, and the hope is that just like what Japan's doing, is they use it to turn off their fast trains, turn off gas lines, things like that. So that was that's a major driver. But the other one that potentially could even be more important after the learning from the Tohoku earthquake is we're through NOAA and their buoys, we're good at looking at tsunamis far offshore. So we can tell when they're coming across the Pacific, but we don't have any, very few pressure measurements that tell us where and the magnitude of tsunamis coming on shore. And so expanding this network with more bottom pressure instruments and seismometers there's a lot of people working on it and trying to get that infrastructure in place. It's not totally cheap. My students always have a discussion about cost benefits, and to install that network is basically the price of a 747, right? So people make decisions. If I could be, you know, we all have our biases, but I would like to be more proactive in protecting the people in the Northeast in Western Washington, right? And along the coast, so, and Oregon. So anyway, that's what I would do. But we're getting there. There's a lot more. And also, I'll just say one more thing is that there is a huge technology for submarine fiber optic cables is just going crazy. And they're starting to, fibers deform very easy, very micro deformation. And so there's experiments starting Monday at the Pacific City Shore Station with our equipment, where for 4 days they're gonna do a different use of the fiber, and basically for 100 kilometers, they'll basically turn that 100 kilometers of cable into 300 sensors and look at seismic activity, how waves come ashore, all sorts of different information. So it's a brand new technology that will be the first community experiment of its kind. So really, I'm so optimistic about the technologies to look at our oceans right now. So sorry for the long answer. So.
No, that's great. Thank you. One of the things that is really inspiring about this project is that it leaves room for so much collaboration. It brings in so many different disciplines. And so I'm looking forward to seeing what new discoveries come of it in the future too. We have a couple questions or comments about the deep sea mining. Do you have anything else to say about any disaster movie-like issues, any environmental issues with that?
Well, environmentally, it will be a disaster, right? You can't get around it. I think it's I share with my students that that's something they're going to have to deal with. It's coming. And, you know, my own view is if we didn't toss so much stuff away, you know, for example, there's a lot of metals, a lot of the trace elements that people want from the seafloor in our phones, and they go whatever, right? And so if we could recoup a lot of the basic metals that are hard to get now because we've used them up on land, we would be a lot farther ahead in having to mine the oceans. Most of the seafloor is, if you look at a map of, you know, think about the gold rush and people staking claims, there's gigantic portions of the seafloor that are now staked out. I don't really want it to happen. I think it's going to be a while before it's economically feasible. One company that was taking the lead for quite a few years in mining a very active hydrothermal system in Papua New Guinea, they went bankrupt. And part of the reasons I am so actively not in favor right now, there's many reasons, but because I think a lot of it's going to go around in third world areas that impact the local environment a lot. And there's fundamental societal financial drivers, but you know, I just really worry about the impact on the local oceans and the people around it, and that it can't just be driven for financial reasons. And also because, in fact, we know so little about these environments. So before we're going to mine something, one, you need to make sure that that technology is there to do it. And two, what is the real impact? And I think there's going to be got to be a lot of real detailed investigations to look at the trade-offs. And maybe someday we will have to do it, right? But I sure hope that we we look for other ways to recover things that we already have in our hands before we have to go there. So.
Yes, well said. The last question I see here is for me about whether it's being recorded and will be shared in the future. And the answer is yes, it's recorded. I'll send out a link to everyone who registered, and I can include any links if you want to pass those along to me, Deb, and then I can get them out to everyone.
I can share the interactive oceans, and please, I get a lot of emails, but please email me if you have any questions or you want to find out anything more. And if I don't respond soonish, then just email me again. I'll be happy to. It's, you know, if you can tell, I'm passionate about it and want to share stuff. So any questions, I'll be glad to answer. And if you have students or kids, I'm more than delighted to. I go give a lot of talks in classrooms too. So.
All right, well, thank you again. This has been about a year in the making, just timing hasn't worked out. I was on maternity leave, Deb was out to sea, so I'm so happy that this was finally able to happen.
Thank you for inviting me. So
yes, thank you.
Be safe in the monsoon.
All right, everyone have a good night.
Take care.